Lay down now. Let your body sink into the softness beneath you and close your eyes. Let the world fade around you and allow your mind to drift slowly into the quiet vastness of space. Tonight, we will journey into the hidden corners of the universe, exploring something you cannot see, but which holds everything you know together. Join us every night for a new documentary. Subscribe and comment with your city or country. Also, we're curious. What time is it there right now? Just one last thing I need to ask before we dive in. What is the substance that outweighs everything we can see, yet remains invisible to our eyes? This question first arose more than a century ago, when astronomers began to notice a puzzling discrepancy between the matter they could detect and the gravitational effects they observed in the universe. In the early decades of the 20th century, careful observations of stars in galaxies and the motion of galaxies themselves revealed an unexpected truth. Much of the mass of the universe was missing from sight. Stars, gas, and dust accounted for only a small fraction of the gravity that kept galaxies intact. One of the earliest signs came from studies of galaxy clusters. Astronomers like Fritz Zwicky measured the velocities of galaxies in the Coma cluster in the 1930s and noticed that the galaxies moved far faster than could be explained by the visible matter alone. According to the laws of gravity known at the time, these clusters should have flown apart, yet they remained bound together. Zwicky concluded that there must be some form of unseen mass providing the necessary gravitational pull. He called it dunkle Materie, or dark matter. At the time, his claim was met with skepticism. Observations were limited, and the tools for detecting invisible mass were crude by modern standards. Nevertheless, the idea lingered quietly in the scientific consciousness, waiting for further evidence. Decades later, in the 1970s, Vera Rubin and her collaborators provided some of the most compelling evidence for dark matter through careful measurements of spiral galaxies. They observed the speed at which stars orbited the centers of their galaxies, expecting to see a decline in speed with increasing distance from the core. Instead, they found that the rotation curves of galaxies remained flat far beyond the regions filled with stars. This implied that the gravitational pull did not drop off as expected, meaning that much more mass existed than could be detected by visible light. Whatever this mass was, it could not be seen through telescopes. It was invisible, yet undeniably present. These observations were not limited to a few unusual galaxies. The pattern repeated across countless spiral galaxies. It became increasingly clear that a mysterious form of matter permeated the universe, outnumbering ordinary matter by a significant margin. The term dark matter entered common scientific usage as a way to describe this unseen mass. It is called dark, not because it absorbs light in the way dust clouds do, but because it emits no light of any kind that we can detect with our instruments. Its presence is inferred entirely through its gravitational influence. It is the silent scaffold upon which galaxies are built. Without it, the spiral arms of galaxies would not maintain their shape, and clusters of galaxies would drift apart. The discovery of dark matter represented a profound shift in our understanding of the universe. The cosmos we see is only a fraction of what truly exists, and the invisible majority plays a crucial role in shaping the structures we observe. As astronomers refined their techniques, evidence for dark matter grew more compelling. Observations of galactic rotation, gravitational lensing, and the motions of galaxy clusters consistently pointed to an invisible mass. The patterns were not random or local. They followed a universal principle. Dark matter appeared to form extensive halos surrounding galaxies, extending far beyond the visible stars and gas. These halos provided the extra gravity needed to explain why galaxies did not fly apart under their own rotation. In essence, dark matter acts as an invisible hand, holding the luminous matter in place. Its distribution is not uniform, but concentrated around galaxies and clusters, subtly shaping the cosmic landscape. The realization that dark matter exists brought with it new questions. What is it made of? How much of it is there? Could it interact with normal matter in ways we have yet to detect? At this stage, the focus was primarily observational, measuring the effects of dark matter on visible structures. Every rotation curve measured, every galaxy cluster observed, confirmed that something unseen was exerting a measurable force. Astronomers began to map the inferred dark matter, constructing models of halos that surrounded galaxies and traced the web-like patterns connecting clusters. These models revealed that the universe's structure is deeply influenced by this invisible component. Filaments of dark matter appear to guide the formation of galaxies along their length, forming a cosmic web that stretches across hundreds of millions of light years. The early observations also highlighted the scale of the mystery. Ordinary matter, the stars, gas, dust, and planets, accounts for only about 1/6 of the universe's total matter content. The remaining 5/6 is dark matter. In other words, everything we see, everything familiar, floats within a far larger sea of invisible substance. It is a humbling realization. When we gaze at the night sky, we see only a portion of the universe's mass. Dark matter remains hidden, but its influence is profound. It dictates the movement of galaxies, the formation of clusters, and the large-scale structure of the cosmos. Its gravity shapes the universe in ways that are directly observable, even if its form remains elusive. Observational astronomy has continued to provide more evidence. Galaxy surveys map large-scale structures, revealing the dense knots and filaments formed by dark matter's gravitational influence. X-ray observations of hot gas in clusters indicate more mass than visible matter alone can account for. Gravitational lensing, the bending of light by massive objects, provides a direct probe of dark matter's distribution, allowing scientists to see its presence without detecting any emitted light. These techniques collectively build a consistent picture. The visible universe is embedded within a far larger, unseen framework. This first segment, the discovery of dark matter, establishes the foundation for understanding the invisible architecture of the cosmos. It demonstrates that what we see is only part of the story, and that the majority of matter in the universe remains hidden, detectable only through its gravitational effects. Observers over the past century have built a compelling case through careful measurement, precise calculation, and patient accumulation of evidence. Dark matter is no longer a speculative idea. It is a fundamental component of the universe, shaping everything from the smallest galaxies to the largest cosmic structures. As we continue our journey, we will explore the ways gravity interacts with this hidden mass, how it forms halos, how it structures the universe, and the ongoing search to understand its true nature. Gravity is the invisible thread that holds the universe together. Every object with mass exerts a pull on every other object, and this force, though invisible, shapes the movement of stars, planets, and galaxies. On Earth, gravity keeps our feet on the ground and guides the orbit of the Moon around our planet. In the vast reaches of space, gravity orchestrates motions on scales far larger than any human can imagine. It controls the paths of stars within galaxies, the paths of galaxies within clusters, and the formation of immense cosmic structures spanning millions of light years. Understanding how gravity works at these cosmic scales reveals why the universe appears organized in the way we observe, and it also shows us why dark matter must exist. Newton's laws of motion and universal gravitation provided the first clear understanding of how objects attract one another. These laws allowed astronomers to predict the movements of planets with remarkable accuracy. They could calculate the orbit of Mercury or the timing of comets returning to the inner solar system. Applying these same principles to stars in galaxies seemed straightforward. The mass of visible stars should determine their orbital speeds. Near the center of a galaxy, where stars are densely packed, gravity should be strong and stars should move rapidly. Farther from the center, as the density of visible stars drops, gravity should weaken and orbital speeds should decline. This expectation formed the basis of astronomical predictions for decades. Yet careful observations told a different story. In the 1970s, astronomers measured the speed of stars at various distances from the centers of spiral galaxies. Instead of slowing down in the outer regions, stars maintained nearly constant speeds, even far beyond the regions populated by visible stars. This behavior contradicted the predictions of Newtonian gravity applied solely to visible matter. If only the matter we could see existed, galaxies would not hold together. Stars in the outskirts should drift outward, leaving galaxies to disperse over time. The fact that galaxies remained intact suggested that some additional unseen mass exerted a gravitational pull strong enough to maintain stability. Gravity alone still explained the motion, but the source of the gravitational force was hidden from direct observation. Clusters of galaxies revealed the same puzzle on an even larger scale. Within a cluster, hundreds or thousands of galaxies orbit a common center of mass. Observations showed that the speed of these galaxies was too high to be explained by the mass of the visible galaxies alone. Using only visible matter, these clusters should fly apart, unable to resist the outward motion of their members. Instead, they remained bound. Zwicky's measurements decades earlier had hinted at this discrepancy, but continued studies confirmed it. Across countless clusters, the gravitational pull observed could not be accounted for by visible matter. The problem was not local or limited to a few unusual cases, it was universal. The stability of galaxies and clusters without additional mass became an unavoidable conclusion. Ordinary stars, gas clouds, and planets simply do not provide enough gravity to hold these structures together. For galaxies to maintain their shape over billions of years, an invisible form of mass must be present, creating an unseen but powerful gravitational field. This hidden mass, which astronomers now call dark matter, acts like glue, binding stars and galaxies in their orbits. Without it, the elegant spirals, the dense cores, and the broad clusters we observe would unravel over cosmic time. Dark matter does not emit or absorb light, yet its gravitational influence is unmistakable, detectable in every rotation curve, velocity measurement, and lensing map. Gravity also governs the formation of cosmic structures from the very beginning. Small fluctuations in density in the early universe were amplified by gravitational attraction. Regions with slightly more mass pulled in surrounding material, growing over millions of years into galaxies, clusters, and filaments. Without sufficient mass to create strong gravitational wells, these structures could not form as they did. Dark matter provides the majority of this mass, deepening the wells and guiding the accumulation of ordinary matter. In this sense, gravity and dark matter work together to shape the cosmic landscape. Dark matter defines the skeleton, and ordinary matter traces its contours, forming stars, gas clouds, and galaxies along the invisible scaffolding. The influence of gravity extends to galaxy interactions. When galaxies collide or pass near each other, their stars follow, predictable paths determined by gravitational forces. Yet the visible mass alone cannot explain the observed motions during such encounters. The presence of dark matter halos alters trajectories, affects the formation of tidal streams, and changes the long-term evolution of interacting systems. Gravity, acting through both visible and invisible mass, governs the fate of these galaxies, ensuring that their structures survive and evolve over billions of years. Observing these interactions provides further evidence of dark matter's gravitational role. Measuring gravity on these cosmic scales relies on careful observation and sophisticated techniques. Astronomers track the motion of stars within galaxies, galaxies within clusters, and gas clouds across intergalactic space. They analyze orbital speeds, accelerations, and lensing effects to infer the total mass present. Every observation consistently shows that visible matter accounts for only a fraction of the gravitational influence. The remaining majority must be invisible, yet its pull is clear and measurable. Gravity reveals the unseen, mapping a universe dominated by matter that cannot be detected with ordinary instruments. Even within individual galaxies, the influence of gravity combined with dark matter is evident in the vertical motion of stars above and below the galactic plane. Stars oscillate up and down as they orbit the galaxy, and the speed of these oscillations is higher than can be explained by the visible disk alone. Dark matter halos provide additional gravitational pull, maintaining stability in 3 dimensions. Without this unseen mass, the structure of the galaxy would be thinner, less stable, and prone to disruption. Gravity, assisted by dark matter, ensures that galaxies maintain their shape across time. Gravity also explains the formation of spiral arms. These arms are not solid structures, but regions of enhanced star density, shaped by gravitational interactions between stars and clouds of gas. Dark matter halos extend far beyond the visible disk, influencing the rotation speed and allowing spiral patterns to persist over billions of years. Without the extra gravitational support, these patterns would wind up and disappear. Gravity, through the unseen mass of dark matter, preserves the symmetry and coherence of these majestic features. The evidence extends beyond isolated galaxies. Observations of the motions of satellite galaxies, such as the Magellanic Clouds around the Milky Way, reveal additional gravitational influence beyond visible stars. Dark matter accounts for these deviations, explaining why satellite galaxies move faster or follow unexpected paths. Gravity, acting on all scales, consistently indicates the presence of a dominant invisible mass. This pattern repeats throughout the observable universe, reinforcing the conclusion that dark matter is an essential component of cosmic structure. In clusters and superclusters, the role of gravity becomes even more pronounced. Dark matter forms the majority of the mass within these vast assemblies, ensuring that galaxies remain bound over immense distances. Gravitational lensing, which bends light around massive objects, provides a direct measure of mass independent of luminosity. These lensing maps consistently show mass where no light is visible, confirming that dark matter governs the gravitational behavior of the largest structures. Gravity, as observed through these effects, points to an unseen yet dominant force shaping the universe. Understanding gravity at cosmic scales thus reveals the necessity of dark matter. Newtonian expectations based solely on visible matter cannot account for the motions of stars, galaxies, or clusters. The problem of galaxy stability is resolved by invoking an invisible component that exerts gravitational pull without emitting light. Dark matter functions as the universe's glue, binding structures together, guiding formation, and ensuring stability across billions of years. Gravity and dark matter together create a universe that is coherent, structured, and enduring, even when most of the mass remains unseen. Through every observation, from the smallest stellar orbits to the motions of entire clusters, gravity points to the same conclusion. The visible universe is only part of the story. An invisible framework of dark matter provides the underlying structure, holding galaxies together and shaping their evolution. The gravitational pull of this hidden mass is subtle yet pervasive, influencing the cosmos on every scale. As we continue our exploration, this understanding forms the foundation for examining how dark matter organizes into halos, how it interacts with visible matter, and how it defines the very shape of the universe we observe. Galaxies come in many shapes and sizes, but two of the most common forms are spiral and elliptical. Spiral galaxies, like our own Milky Way, have flat, rotating disks filled with stars, gas, and dust. They are often adorned with sweeping arms that spiral outward from a dense central bulge. Elliptical galaxies, by contrast, are more rounded, with stars distributed in a smooth ellipsoidal shape. They lack the well-defined disk and arms of spiral galaxies, and often contain less gas, making them less active in forming new stars. Despite these differences, both types of galaxies share a common need. They require far more mass than can be seen to remain stable over time. Observations of rotation and velocity reveal this hidden necessity in striking detail. In spiral galaxies, stars orbit the galactic center at varying distances. Classical calculations predict that stars near the center, where visible mass is concentrated, should orbit quickly, while stars farther out in regions with fewer visible stars should slow down. Early observations, however, showed that stars in the outer regions moved at nearly the same speed as those closer in. These flat rotation curves could not be explained by the gravity of visible matter alone. The stars behaved as if the galaxy contained additional mass extending well beyond the luminous disk. This mass could not be seen, yet its gravitational influence was unmistakable. Spiral galaxies thus provide some of the clearest evidence that an invisible, massive component surrounds visible matter, keeping stars in their steady orbits. Elliptical galaxies present a different but complementary story. They lack the ordered rotation of spirals, and their stars move more randomly, orbiting in various directions around the galaxy's center. Astronomers measure the velocities of these stars to infer the galaxy's total mass. When these measurements are compared with the mass visible in stars and gas, the difference is striking. Elliptical galaxies, like spirals, require the presence of large amounts of unseen matter to account for the observed motions. This unseen mass, forming a halo around the galaxy, provides the gravitational binding necessary to prevent the stars from dispersing into space. In both spiral and elliptical galaxies, the evidence points to a common structure, an extensive, invisible halo enveloping the luminous material. The concept of a dark matter halo describes a roughly spherical region of unseen mass that extends beyond the visible edge of a galaxy. These halos are not uniform, but have density that decreases gradually with distance from the galactic center. They are thought to contain the majority of a galaxy's mass, outnumbering visible stars by several times. The halo exerts gravitational influence on all visible components, from the central bulge to the outermost gas clouds. Without it, the galaxy could not maintain its structure over billions of years. Halo models are critical to understanding the distribution of dark matter, its interaction with ordinary matter, and its role in shaping galaxies. Observational evidence for dark matter halos comes from multiple sources. Rotation curves in spiral galaxies show that orbital speeds remain high at large radii, indicating the presence of mass well beyond the visible disk. Velocity dispersion measurements in elliptical galaxies provide similar conclusions. Stars move faster than visible matter can explain. In clusters of galaxies, the velocities of individual galaxies require additional mass to hold the cluster together. Gravitational lensing, which bends light around massive objects, maps the total mass, revealing halos that extend far beyond the regions of visible stars. Collectively, these observations confirm that dark matter halos are real and dominant structures in galaxies. The distribution of mass within these halos is often described using the Navarro-Frank-White, or NFW, profile. This model, derived from numerical simulations of cold dark matter, provides a simple way to represent how density changes with distance from the galactic center. Near the center, the density is higher, gradually declining toward the outskirts. The NFW profile captures the essential shape of dark matter halos, allowing astronomers to model the gravitational potential and predict rotational velocities and velocity dispersions. While real galaxies may vary from the idealized profile, the NFW model offers a baseline that aligns closely with observations and simulations, connecting theory with measurable properties. These halos are enormous, stretching well beyond the luminous edge of a galaxy. In some cases, they may extend hundreds of thousands of light years from the center, far beyond where stars or gas are detectable. The total mass contained within a halo is often many times greater than the mass of visible stars. This massive invisible component dominates the gravitational field of the galaxy, dictating the motion of stars, gas, and even satellite galaxies. The halo provides a protective framework, ensuring that galaxies remain stable and coherent as they rotate, interact with neighbors, and evolve over cosmic time. Dark matter halos also influence the formation and survival of galactic structures. In spiral galaxies, halos help preserve the shape of disks and the coherence of spiral arms. Without the additional gravitational pull from the halo, the disk would be prone to warping or disruption. In elliptical galaxies, Halos maintain the gravitational binding necessary for stars moving in random directions to remain contained. In both cases, the halo functions as a gravitational anchor, an unseen but essential element that stabilizes the visible galaxy against internal motions and external perturbations. The presence of these halos explains why galaxies, despite their complexity and the diversity of their forms, maintain integrity over billions of years. Observations of satellite galaxies and globular clusters further illustrate the halo's influence. These smaller objects orbit the main galaxy under the gravitational pull of the combined visible and invisible mass. Their trajectories, speeds, and distributions provide additional data to map the halo's shape and extent. In many cases, satellite galaxies move faster or along paths that cannot be explained by visible matter alone. Dark matter halos create the gravitational environment necessary to sustain these motions, revealing the vast scale and reach of the unseen component. Each new measurement reinforces the idea that galaxies are not isolated systems of stars, but structures embedded within larger, invisible gravitational envelopes. The study of halos also connects to galaxy formation. In the early universe, dark matter halos acted as gravitational wells, attracting gas and dust that later condensed into stars. The size and density of the halo influenced the rate of star formation and the ultimate mass of the galaxy. Halos provide a stable environment, preventing gas from escaping too quickly and allowing galaxies to grow gradually. Over billions of years, the interplay between dark matter halos and ordinary matter shaped the morphology, size, and dynamics of the galaxies we observe today. Without halos, galaxies would be smaller, less organized, and unable to sustain the patterns we see in spiral arms or the smooth distributions in elliptical systems. Simulations of galaxy formation reinforce these observations. By modeling the behavior of dark matter and ordinary matter together, astronomers can reproduce the rotation curves, velocity dispersions, and overall structures of real galaxies. These simulations show that halos form naturally from the collapse of dark matter under gravity, providing the gravitational framework necessary for visible matter to accumulate. Spiral disks, central bulges, and elliptical spheroids all arise within these halos, illustrating the deep connection between dark matter and galactic architecture. The match between simulations and observation provides strong evidence for the existence and importance of halos. Dark matter halos are not passive structures. They influence galactic interactions as well. When galaxies merge or pass near each other, the halos affect tidal forces, orbital decay, and the distribution of stars and gas. Halos can absorb energy and momentum during encounters, preserving the overall structure of the galaxies, while allowing visible matter to interact more dynamically. Observing these interactions helps map the extent and mass of halos, revealing subtle features that confirm their gravitational dominance. The halos, though invisible, are fundamental actors in the ongoing evolution of galaxies. In summary, dark matter halos form the invisible scaffolding of galaxies. Whether in spirals or ellipticals, they extend far beyond the luminous regions, providing the gravitational support necessary for stability and coherence. Observations of rotation curves, velocity dispersions, satellite motions, and gravitational lensing all point to their presence. The NFW profile offers a simple yet effective description of their density distribution, while simulations show how halos guide the formation and evolution of galaxies. These halos are the quiet, unseen structures that hold together the grand patterns of stars we observe, the gravitational glue that maintains the universe's order. Beyond individual galaxies lie clusters, vast gatherings of hundreds or even thousands of galaxies bound together by gravity. These clusters are among the largest structures in the universe, spanning millions of light-years across space. They serve as natural laboratories for studying dark matter because their enormous mass magnifies the gravitational effects of invisible matter, making it easier to observe indirectly. Each galaxy within a cluster moves under the combined gravitational pull of all the others. But the visible matter alone is insufficient to explain the observed motions. The stars and gas we can see account for only a fraction of the gravitational binding, implying that a dominant, unseen mass holds the cluster together. Studying these massive systems allows astronomers to map dark matter on scales far larger than individual galaxies, providing insight into its distribution, quantity, and influence. One of the most powerful tools for detecting and mapping dark matter in clusters is gravitational lensing. Predicted by Einstein's theory of general relativity, gravitational lensing occurs when a massive object bends the path of light from a more distant source. The light does not travel in a straight line, but curves around the gravitational field of the intervening mass. When astronomers observe these distortions, they can calculate the total mass required to produce them, regardless of whether it emits light. Lensing comes in two forms: strong and weak. Strong lensing produces dramatic visual effects, such as multiple images of the same galaxy, arcs, or rings. Weak lensing is subtler, causing slight distortions in the shapes of many background galaxies that can be statistically measured to reveal the mass distribution of the foreground cluster. Galaxy clusters demonstrate both types of lensing. In clusters with a particularly concentrated mass, the light from background galaxies can form large arcs, stretched images, and even Einstein rings, all visible in telescope images. These strong lensing effects allow astronomers to pinpoint areas of high mass concentration, often corresponding to dense clumps of dark matter. Weak lensing, on the other hand, provides a more global view. By examining the shapes of thousands of faint background galaxies, scientists can create detailed maps showing how mass, both visible and invisible, is distributed throughout the cluster. These lensing maps are among the most direct methods of detecting dark matter, offering a way to visualize the invisible. One of the most famous cases illustrating the power of lensing is the bullet cluster. This system consists of two galaxy clusters that collided at high speed. Observations reveal that the hot gas, which emits X-rays and accounts for much of the visible baryonic mass, is slowed and disrupted by the collision. The galaxies, however, pass through more freely, and the gravitational lensing maps show that the majority of the mass is not coincident with the visible gas, but instead follows the distribution of the galaxies. This separation between ordinary matter and gravitational mass provides one of the clearest pieces of evidence that dark matter exists independently of the material we can see. The bullet cluster illustrates that dark matter interacts weakly with itself and ordinary matter, affecting gravitational dynamics while remaining invisible in electromagnetic observations. Other clusters also provide insight into dark matter through lensing. The Abel clusters, for example, show a variety of mass distributions, where lensing maps indicate large halos surrounding the visible galaxies. These halos often extend far beyond the bright cores, demonstrating that dark matter dominates the mass budget even in regions with few stars. Observations of multiple clusters across the sky consistently reinforce the pattern. The majority of mass is unseen, yet its gravitational influence shapes the motion of galaxies, the bending of light, and the stability of clusters. Each new observation confirms the essential role of dark matter in the architecture of the universe. Gravitational lensing allows astronomers not only to detect dark matter, but also to measure its quantity and distribution with remarkable precision. By combining strong and weak lensing observations, scientists can construct detailed three-dimensional maps of cluster mass. These maps reveal where dark matter is concentrated, how it is distributed around galaxies, and how it forms halos that extend far beyond visible light. The shapes of these halos and the clumping patterns within them provide clues about the nature of dark matter itself, including how it interacts, its density profile, and its influence on cosmic structure formation. In this way, lensing transforms the invisible into something measurable and comprehensible. Clusters also reveal the interplay between dark matter and ordinary matter. The visible galaxies and hot gas are only minor contributors to the total mass. Hot gas emits X-rays, which can be observed with space-based telescopes, and the stars in galaxies emit visible and infrared light. Together, they represent a fraction of the gravitational mass revealed by lensing. Dark matter dominates the dynamics, guiding the movement of galaxies, shaping the hot gas, and influencing future mergers. The distribution of dark matter within clusters provides a framework that determines how galaxies interact, merge, and evolve over billions of years. Detailed studies of lensing across many clusters have revealed common patterns. Dark matter forms extended, roughly spherical halos around clusters, with denser cores and gradually decreasing density outward. Within these halos, smaller clumps of dark matter may exist, corresponding to individual galaxies or substructures. Lensing allows astronomers to detect these subhalos, confirming predictions from simulations of cold dark matter. The ability to observe these clumps is crucial, as it shows that dark matter is not uniform but structured, influencing both large-scale cosmic architecture and smaller-scale galactic interactions. Cluster observations also provide insight into the history of the universe. The distribution of dark matter in clusters reflects the cumulative effect of gravitational collapse over billions of years. Regions of higher density formed first, attracting more matter and growing into the clusters we observe today. Lensing maps of distant clusters show mass distributions that are consistent with the growth of structure in a universe dominated by dark matter. By comparing clusters at different distances, and therefore at different cosmic times, astronomers can trace the evolution of dark matter and the formation of large-scale structures, providing a bridge between local observations and the history of the cosmos. The bullet cluster is not the only system providing such clarity, but it is among the most illustrative. Other colliding clusters, such as the train wreck cluster and Abell 520, also show separations between visible gas and gravitational mass, reinforcing the evidence for dark matter's existence. These collisions are natural experiments, revealing how dark matter behaves in extreme conditions. In every case, lensing shows that the majority of mass is invisible, forming halos that guide the motion of visible galaxies and gas. Through these observations, scientists have built a consistent picture Dark matter is real, massive and pervasive, forming the backbone of the largest structures in the universe. Clusters also provide a way to study dark matter's interaction, or lack thereof, with itself. The fact that dark matter passes through collisions with little friction or disruption suggests that it interacts primarily through gravity, not through electromagnetic forces or strong collisions like ordinary matter. This behavior is critical in understanding why halos remain stable over time, why they extend beyond the luminous matter, and why galaxies within clusters maintain their relative positions. Observations of lensing and cluster dynamics together create a coherent framework describing both the presence and properties of dark matter in these enormous systems. Finally, gravitational lensing allows for the combination of multiple data sources to refine our understanding of dark matter. Observations of X-ray gas, the motions of galaxies, and lensing distortions together paint a comprehensive picture of cluster mass. Each method corroborates the others, showing that visible matter alone is insufficient to explain the gravitational effects observed. By measuring the lensing distortions across wide fields, astronomers can trace the shape of the dark matter halo, identify substructures, and even estimate the total mass of the cluster. The result is a detailed, multidimensional map of invisible mass, a window into the otherwise hidden architecture of the universe. Through clusters and gravitational lensing, we can see the immense power of dark matter in shaping cosmic structure. Clusters serve as laboratories, where the invisible becomes measurable, where the hidden majority reveals itself through gravitational effects. Strong lensing captures dramatic distortions that trace dense cores, while weak lensing maps subtle changes across millions of light years. The bullet cluster and similar systems provide clear visual evidence that mass exists where no light shines, confirming the reality and dominance of dark matter. Lensing maps reveal halos, substructures, and distribution patterns, transforming abstract theory into observable phenomena. In this way, clusters of galaxies allow scientists to study dark matter directly, offering a glimpse into the unseen framework that holds the universe together. Long before galaxies formed, the universe was filled with hot, dense plasma, a mixture of photons, protons, electrons, and dark matter. This was the early universe, just hundreds of thousands of years after the Big Bang, when light could not travel freely because it scattered constantly off charged particles. As the universe expanded and cooled, photons gradually decoupled from matter, streaming freely through space. These ancient photons form the cosmic microwave background, or CMB, a faint glow detectable in every direction. The CMB is not uniform. It contains tiny variations in temperature and density imprinted by the conditions of the early universe. Studying these fluctuations provides a window into the nature of matter, including the invisible dark matter that dominates the cosmic mass budget. The CMB carries a detailed record of how matter was distributed shortly after the universe became transparent to light. Dark matter, which does not interact with photons, began to form gravitational wells even before ordinary matter could condense. Regions with slightly higher dark matter density attracted surrounding particles, amplifying small variations in the distribution of matter. These primordial fluctuations seeded the large-scale structures that would later grow into galaxies, clusters, and filaments. By examining the tiny temperature differences in the CMB, scientists can infer the distribution of dark matter in the early universe and understand how it influenced the formation of cosmic structures. Satellite missions such as COBE, WMAP, and Planck have measured the CMB with extraordinary precision. These observations reveal fluctuations on scales of fractions of a degree across the sky, corresponding to density variations in the early universe. By analyzing these patterns, scientists can determine the proportion of matter that was ordinary versus dark. The CMB shows that ordinary matter makes up a small fraction of the total mass, while dark matter dominates. These measurements align closely with other evidence from galaxy rotation curves, lensing, and cluster dynamics, creating a consistent picture of a universe filled mostly with invisible mass that shaped its evolution from the very beginning. The influence of dark matter on the early expansion of the universe is profound. During the first millions of years, dark matter's gravitational pull affected the rate at which regions of the universe grew denser or remained diffuse. Without dark matter, density fluctuations would have grown more slowly, and structures like galaxies and clusters might not have formed as quickly or at all. The presence of dark matter accelerated the aggregation of matter in specific regions, guiding the formation of cosmic filaments and walls. This gravitational scaffolding allowed ordinary matter to follow, condensing into stars and galaxies within the dark matter framework. Primordial fluctuations in density, influenced heavily by dark matter, are key to understanding the patterns we observe today. Slight differences in density caused small variations in temperature in the CMB. The colder spots represent slightly denser regions, where gravity had pulled matter inward, while warmer spots correspond to less dense regions. These fluctuations were incredibly small, often only 1 part in 100,000, but they set the stage for the universe's large-scale structure. Dark matter amplified these differences, creating potential wells that ordinary matter would later occupy. The connection between dark matter and primordial fluctuations is central to cosmology, showing that the invisible mass shaped the cosmos even before the first stars formed. The CMB also informs us about the total amount of matter in the universe. By analyzing the spectrum of fluctuations, scientists can estimate the density of dark matter relative to ordinary matter. The results consistently indicate that dark matter constitutes about 5 times more mass than ordinary matter. These estimates match predictions from other lines of evidence, reinforcing the conclusion that the universe is dominated by invisible mass. The CMB thus acts as both a historical record and a diagnostic tool, allowing cosmologists to study dark matter indirectly through the imprint it left on the oldest light in the universe. Large-scale structure formation is closely tied to dark matter. As the universe expanded, regions of higher dark matter density grew into filaments and clusters, creating a cosmic web. Ordinary matter, interacting through both gravity and electromagnetic forces, flowed along these dark matter structures. Gas collected in the densest regions, cooled, and eventually formed stars and galaxies. Observations of galaxy surveys show that galaxies are not randomly distributed, but trace these filaments, supporting the model in which dark matter forms the underlying framework. Without dark matter, the cosmic web would be far less pronounced, and the universe would appear more uniform and featureless. The timing of structure formation is also influenced by dark matter. Because it interacts primarily through gravity, dark matter could begin clustering earlier than ordinary matter, which was coupled to radiation in the early universe. These early clumps of dark matter provided the seeds for galaxies to form, as ordinary matter fell into the gravitational wells. The sequence of events explains why galaxies and clusters formed relatively quickly in cosmic history, and why their distribution matches the patterns predicted by simulations that include dark matter. Observations of distant galaxies at high redshift confirm that structures were already forming when the universe was only a few billion years old, consistent with the influence of dark matter from the earliest times. The CMB further reveals information about the geometry and expansion rate of the universe. Tiny variations in the background radiation provide clues about the total mass-energy content, including dark matter, dark energy, and ordinary matter. Dark matter's gravitational influence affects the growth of these fluctuations over time, shaping the peaks and troughs observed in the CMB power spectrum. By studying these features, cosmologists can constrain models of the universe, measure the fraction of dark matter, and understand how the expansion and structure formation are interconnected. The CMB is thus a critical tool linking the invisible dark matter to observable features in the cosmos. Primordial fluctuations also explain the variations in cluster mass and galaxy density. Regions with more dark matter attracted more ordinary matter, leading to higher star formation rates and denser galaxy clusters. Areas with less dark matter remained relatively empty, forming cosmic voids. This uneven distribution underlines the role of dark matter in creating the universe's large-scale structure. Observations of these patterns today, combined with CMB measurements, allow scientists to reconstruct the initial conditions and trace how dark matter influenced the growth of cosmic structures over billions of years. By examining the CMB and its subtle fluctuations, astronomers can also test different dark matter models. Cold dark matter, which moves slowly compared to the speed of light, produces a specific pattern of density fluctuations and large-scale structures that matches observations. Hot, dark matter moving quickly would have smoothed out small-scale fluctuations, preventing the formation of smaller structures like galaxies. The success of cold dark matter in reproducing the observed universe reinforces the idea that dark matter interacts primarily through gravity without significant collisions or radiation. The CMB thus provides a snapshot of dark matter's behavior at the dawn of cosmic time. The interplay between dark matter and ordinary matter in the early universe also explains the observed distribution of galaxies today. Dark matter clumps guided the inflow of gas, influencing galaxy size, shape, and star formation rates. Regions with more dark matter formed larger, denser galaxies, while less dense regions produced smaller or fewer galaxies. The cosmic web traced by dark matter determines where galaxies cluster and where voids exist, connecting early fluctuations to modern structure. The CMB acts as a bridge, linking the unseen mass of the early universe to the complex arrangement of galaxies across billions of light years. In this way, the cosmic microwave background provides a detailed, measurable record of dark matter's role in shaping the universe. It shows how dark matter influenced the early expansion, seeded structures, and guided the distribution of ordinary matter. Fluctuations in the CMB, though minute, reveal the gravitational fingerprint of dark matter, connecting the present-day cosmic web to its earliest origins. By studying the CMB, scientists can trace dark matter's influence across space and time, understanding how the invisible majority of matter has governed the evolution of the universe from the first moments to the structures we observe today. Dark matter is a broad term that describes any mass in the universe that does not emit or absorb light, yet exerts a gravitational influence. To understand its nature, scientists divide potential candidates into two main categories: baryonic and non-baryonic matter. Baryonic matter consists of the familiar particles that make up stars, planets, and gas, protons, neutrons, and electrons. Non-baryonic matter, by contrast, is composed of particles outside the standard matter we can detect directly. While baryonic dark matter is possible in theory, such as faint stars or black holes, much of the evidence suggests that the majority of dark matter is non-baryonic, composed of unknown exotic particles that interact primarily through gravity. Baryonic candidates for dark matter were studied extensively in the past. Among the simplest ideas were massive compact halo objects, or MACOs. These include objects like brown dwarfs, faint stars, or black holes too small or dim to detect easily. MACOs could contribute to the gravitational pull needed to hold galaxies together. To search for them, astronomers used a technique called microlensing, which observes the slight brightening of background stars when a massive object passes in front. These studies detected some MACOs, but the total number and mass were not enough to explain the full gravitational effects attributed to dark matter. While MACOs exist and account for a portion of the unseen mass, they cannot explain the dominant majority, which must be non-baryonic. Non-baryonic matter is thought to consist of particles that are very weakly interacting, meaning they do not emit, absorb, or scatter light in any measurable way. The leading candidates in this category include WIMPs, or weakly interacting massive particles. WIMPs are hypothetical particles with mass similar to ordinary atomic nuclei, but interact only through gravity and possibly the weak nuclear force. Because they barely interact with normal matter, they are extremely difficult to detect. Experiments on Earth have attempted to observe WIMPs directly by placing detectors deep underground to shield them from cosmic rays and background radiation. Although no definitive detections have been made, WIMPs remain a central focus of research because their predicted properties fit well with the observed behavior of dark matter on galactic and cosmological scales. Another category of non-baryonic candidates includes sterile neutrinos. Neutrinos are lightweight particles that barely interact with normal matter, and sterile neutrinos are a hypothesized form that interacts even less, only through gravity. If they exist, they could account for some portion of dark matter, particularly in the early universe, where their presence could influence the formation of galaxies and clusters. Sterile neutrinos would have subtle effects on structure formation and could leave detectable signals in X-ray observations from the decay of their rare interactions. Like WIMPs, they remain hypothetical but consistent with the known properties required of dark matter. Axions are another theoretical candidate for non-baryonic dark matter. These are extremely light particles proposed to solve certain problems in particle physics, and they could be produced abundantly in the early universe. Axions interact very weakly with ordinary matter and could form a diffuse, cold dark matter component that fills galactic halos. Experiments using strong magnetic fields and sensitive detectors have attempted to convert axions into detectable photons, providing a pathway for potential discovery. If axions exist, they would explain many of the properties inferred for dark matter, including its pervasive, non-interacting nature and role in galactic stability. Other exotic candidates have been proposed over time, ranging from primordial black holes formed in the early universe to more speculative particles predicted by extensions of the standard model of physics. Each candidate must meet strict criteria. It must be massive enough to influence gravity on galactic scales, abundant enough to account for the majority of unseen mass, and sufficiently non-interactive with light to remain invisible in telescopes. By comparing theoretical predictions with observations of rotation curves, gravitational lensing, cluster dynamics, and the cosmic microwave background, scientists narrow down the possibilities. This process has led to the conclusion that dark matter is likely non-baryonic and composed of one or more unknown particles. Direct detection efforts continue to explore these candidates. Deep underground laboratories shielded from cosmic rays search for rare interactions of WIMPs with atomic nuclei. Sensitive detectors attempt to capture axions through their predicted conversion into photons in strong magnetic fields. Observations of neutrinos and X-rays may reveal signatures of sterile neutrinos. Even the search for primordial black holes examines whether these objects could contribute meaningfully to dark matter halos. Each approach tests the properties of dark matter, aiming to connect theory with the invisible mass that dominates galaxies and clusters. Indirect detection provides complementary evidence. Astronomers look for the effects of dark matter particles annihilating or decaying into detectable radiation, such as gamma rays. Observations with space-based telescopes and ground-based observatories scan the galactic center, dwarf galaxies, and other regions expected to have high dark matter density. While results are inconclusive, these studies constrain the properties and abundance of various dark matter candidates, refining our understanding of what it could be. The combination of direct and indirect searches allows scientists to explore multiple hypotheses and rule out options that do not match observations. Computer simulations also help test candidate particles. By modeling the formation of galaxies, clusters, and large-scale structures using different types of dark matter, scientists can compare the results with what is observed in the universe. Simulations assuming cold, non-interacting dark matter, consistent with WIMPs or axions, reproduce the distribution of galaxies and halo structures remarkably well. Simulations with hot or highly interactive dark matter fail to produce the observed clumps and filaments. These comparisons provide indirect support for certain candidates while excluding others, illustrating how astrophysical observations and theoretical physics work together to narrow the search. The interplay between candidate properties and cosmic behavior is crucial. WIMPs, if massive and cold, would cluster effectively, forming the halos required to explain galactic rotation curves. Sterile neutrinos, being lighter and possibly warmer, could influence the formation of smaller structures, affecting the number of dwarf galaxies observed. Axions, being extremely light, would form a nearly uniform background, but could still contribute gravitationally to halos. Each candidate leaves a distinct imprint on the structure and evolution of the universe, allowing astronomers to test hypotheses by comparing predicted effects with observations. Baryonic and non-baryonic candidates differ in detectability. Machos, being made of ordinary matter, could be observed indirectly through microlensing events, whereas WIMPs, axions, and sterile neutrinos require highly sensitive instruments and innovative detection methods. The lack of conclusive macro detections at the necessary abundance points toward non-baryonic candidates as the dominant form of dark matter. The challenge is to identify particles that satisfy both theoretical requirements and observational constraints, a task that continues to drive research in astrophysics and particle physics alike. Each type of dark matter candidate offers unique insights into fundamental physics. Discovering a particle like a WIMP or axion would not only explain galactic rotation curves and cluster dynamics, but also reveal physics beyond the standard model. Sterile neutrinos could connect cosmology with neutrino physics, while primordial black holes would provide clues about conditions in the early universe. Studying these candidates bridges the gap between astrophysics and particle physics, showing that understanding the invisible majority of mass requires collaboration across multiple disciplines. The search for dark matter is thus a central pursuit in modern science, connecting observation, theory, and experiment. The distinction between baryonic and non-baryonic dark matter, along with the wide range of candidates, illustrates the depth of the mystery. While baryonic objects like MACOs account for a small fraction of unseen mass, non-baryonic particles such as WIMPs, sterile neutrinos, and axions likely dominate. The gravitational behavior of galaxies, clusters, and the cosmic web constrains the properties of these particles, shaping the search strategies employed by scientists. Every rotation curve, lensing map, and CMB measurement adds to our understanding, guiding the hunt for the fundamental constituents of the invisible universe. Detecting dark matter on Earth is a complex and ongoing challenge. Because dark matter interacts very weakly with ordinary matter, it passes through most material without leaving a trace. Scientists have therefore developed highly sensitive experiments to try to capture rare interactions. Direct detection experiments aim to observe dark matter particles colliding with atomic nuclei in a detector. These collisions are extremely infrequent and produce only tiny energy signals, so detectors must be isolated from other sources of noise, such as cosmic rays and natural radioactivity. Laboratories are often built deep underground to shield them from interference, creating a quiet environment where the faint effects of dark matter could be observed. One of the leading direct detection experiments is Xenon 1T, located in the Gran Sasso laboratory in Italy. This detector uses a large tank filled with liquid xenon, which serves both as the target and the detection medium. When a dark matter particle collides with a xenon nucleus, it can produce a small flash of light and a slight release of electrons. These signals are amplified and recorded by sensitive instruments, allowing scientists to distinguish potential dark matter interactions from background noise. Despite the enormous effort and extreme sensitivity, no definitive detection has been confirmed, though each experiment places tighter constraints on the properties of possible dark matter particles. Other direct detection experiments include LUX and DAMA. LUX, the Large Underground Xenon Experiment, also uses a xenon-based detector and operates in the United States. It has provided precise limits on the interaction rate and mass of hypothetical dark matter particles. DAMA, on the other hand, is based in Italy and uses sodium iodide crystals to detect annual modulation signals that could indicate dark matter interactions. DAMA has reported a persistent signal over many years, though the interpretation remains debated, and other experiments have not confirmed the findings. Together, these projects represent complementary approaches to capturing the elusive particles, each testing different mass ranges and interaction strengths. Indirect detection methods offer a different path. Instead of waiting for dark matter to collide with nuclei on Earth, scientists look for the products of dark matter annihilations or decays in space. When dark matter particles interact with each other, they may produce gamma rays, neutrinos, or other particles that can be observed with telescopes or detectors on Earth. Observing regions of high dark matter density, such as the center of the Milky Way or dwarf galaxies, provides opportunities to detect these rare signals. While no definitive indirect detection has been achieved, measurements place limits on how dark matter behaves and the types of particles that could constitute it. Gamma-ray telescopes, both in orbit and on the ground, search for excess radiation that could indicate dark matter interactions. High-energy gamma rays can be traced back to dense regions where dark matter is expected to concentrate. Observatories like Fermi-Lat monitor these regions continuously, searching for patterns or spikes in emission that cannot be explained by ordinary astrophysical processes. Neutrino detectors, such as IceCube at the South Pole, look for neutrinos produced by dark matter captured in the Sun or Earth. These neutrinos travel long distances without scattering, providing another indirect signal. By combining data from multiple sources, scientists aim to piece together evidence for dark matter interactions occurring beyond our planet. Collider searches provide yet another avenue. High-energy particle accelerators, such as the Large Hadron Collider at CERN, attempt to create dark matter particles in controlled collisions. By smashing protons together at extremely high speeds, physicists can generate conditions similar to those in the early universe. If dark matter particles are produced, they may escape the detector without interacting, leaving a signature of missing energy and momentum. Scientists carefully analyze these events, searching for deviations from known physics that could indicate the presence of dark matter. So far, collider searches have not detected dark matter, but they provide valuable constraints on particle mass, interaction strength, and other properties. Each of these detection methods faces unique challenges. Direct detection experiments must isolate incredibly weak signals from natural and cosmic backgrounds. Indirect detection relies on distinguishing rare signals from abundant astrophysical sources such as pulsars, supernovae, or cosmic rays. Collider searches must separate possible dark matter events from vast numbers of standard particle interactions. Across all approaches, the common difficulty is that dark matter interacts so rarely and so weakly that finding it requires extreme precision, careful analysis, and often patience over many years. The technological sophistication required is remarkable. Direct detectors use materials purified to remove almost every trace of natural radioactivity. Cryogenic temperatures are maintained to minimize thermal noise. Electronic sensors must be extraordinarily sensitive, capable of detecting tiny flashes of light or minute electron releases. Indirect detection instruments observe the sky across different wavelengths, combining data over years to identify patterns. Collider detectors are massive, multi-layered systems designed to track and identify billions of particles produced in collisions. Every step is aimed at maximizing sensitivity while minimizing false signals, reflecting the difficulty of observing something that interacts so weakly. Despite the challenges, Each experiment contributes essential information. Null results are not failures. They narrow the range of possible properties for dark matter particles. Each measurement refines models, excluding candidates that would have produced detectable signals. Over time, this process sharpens our understanding of what dark matter could be, guiding future experiments. Scientists analyze the results collectively, comparing constraints from direct, indirect, and collider searches to identify regions of parameter space still viable for dark matter candidates, like WIMPs, axions, or sterile neutrinos. Collaboration across the globe enhances these efforts. Experiments in different locations, using different technologies, and targeting different particle masses or interaction strengths provide complementary coverage. This global network ensures that no plausible range for dark matter properties is overlooked. By sharing data, refining techniques, and updating models, the scientific community gradually closes in on the possible candidates. Each experiment, whether it detects a signal or not, adds to the growing map of what dark matter can and cannot be, creating a cumulative body of knowledge essential for eventual discovery. The ongoing search illustrates the patience and ingenuity required in modern science. Dark matter does not reveal itself easily, and its elusive nature demands careful observation, precise instrumentation, and rigorous analysis. The combination of underground detectors, space-based telescopes, and high-energy accelerators represents a multi-pronged strategy designed to capture a phenomenon that does not interact in ordinary ways. While the task is challenging, it has also driven technological advances and deepened our understanding of the universe, even as dark matter itself remains unseen. Through these detection efforts, scientists are gradually constraining the properties of dark matter. Limits on mass, interaction strength, and distribution help refine theoretical models. Experiments that span decades provide increasingly precise data, gradually ruling out candidates or supporting certain particle types. The combined evidence from multiple detection methods ensures that when dark matter is eventually observed directly, the discovery will be robust and well understood. The ongoing search on Earth thus connects laboratory experiments to cosmic phenomena, linking human ingenuity to the unseen mass that dominates galaxies and clusters. Detecting dark matter on Earth is a complex, multifaceted effort. Direct detection experiments search for rare collisions between particles and atomic nuclei deep underground. Indirect detection observes the products of dark matter interactions in space, such as gamma rays and neutrinos. Collider searches aim to produce dark matter in high-energy particle collisions, looking for missing energy signatures. Each approach faces challenges due to the particles' weak interactions and elusive nature. Despite the difficulty, these efforts continue, gradually narrowing the range of possibilities and bringing scientists closer to uncovering the particles that form the invisible majority of matter in the universe. Understanding dark matter's role in shaping the universe often relies on simulations. Scientists cannot manipulate galaxies directly, nor can they observe dark matter in isolation. To study its effects, researchers create computer models that simulate how matter moves and interacts over billions of years. One key method is called n-body simulation. In these simulations, particles represent clumps of dark matter or ordinary matter, and their motion is calculated using the laws of gravity. By observing how these particles evolve over time, scientists can visualize the formation of galaxies, clusters, and larger cosmic structures. N-body simulations begin with the conditions of the early universe, informed by observations of the cosmic microwave background. Small density fluctuations, seeded by primordial variations, provide the initial framework. Dark matter, interacting only through gravity, forms clumps and filaments. Ordinary matter follows these gravitational wells, cooling and condensing into stars and galaxies. The simulations allow scientists to track this evolution step by step, observing how the cosmic web emerges. Dense nodes form at the intersections of filaments, giving rise to clusters of galaxies. Less dense regions become voids, creating the large-scale patterns that resemble what astronomers see when surveying the sky. The effects of dark matter on cosmic structure are profound. Without it, the formation of galaxies would be much slower. Ordinary matter alone could not clump efficiently due to its interactions with radiation in the early universe. Dark matter, unaffected by light, collapses under gravity, creating potential wells that guide the assembly of visible matter. Simulations consistently show that galaxies form within dark matter halos, with their size and shape influenced by the halo's mass and distribution. Spiral galaxies often form in halos with smooth rotation, while elliptical galaxies can result from mergers within more chaotic halos. The presence of dark matter is essential for reproducing the diversity and stability of galactic structures observed in reality. Comparing simulation results with real observations is a critical step in understanding dark matter. Astronomers examine the rotation curves of galaxies, the distribution of clusters, and the filamentary pattern of the cosmic web. Simulations that include cold, non-interacting dark matter produce structures remarkably similar to those observed. The number of dwarf galaxies, the density of halos, and the arrangement of clusters match predictions, providing strong support for the models. When simulations omit dark matter or assume incorrect properties, the resulting universe looks significantly different, with too few structures or incorrect distributions. These comparisons allow scientists to refine both the physics of the models and the assumed properties of dark matter particles. Simulations also explore different dark matter candidates. By adjusting particle mass, interaction strength, and velocity, researchers can study how these properties influence structure formation. For example, warm dark matter with slightly higher velocities suppresses the formation of small galaxies, while cold dark matter allows dense, small-scale clumps to form. Observing which scenarios reproduce real cosmic structures constrains the types of particles that could make up dark matter. In this way, computer models act as a laboratory, testing hypotheses about a substance that cannot yet be observed directly. N-body simulations reveal the hierarchical nature of structure formation. Small dark matter clumps merge to form larger halos, which then host groups of galaxies. These mergers influence galaxy evolution, triggering star formation or reshaping galactic morphology. Simulations demonstrate that dark matter halos retain memory of these mergers, forming extended, roughly spherical structures around galaxies. Observations of halo profiles, such as those described by the Navarro-Frank-White model, match the patterns produced in simulations, confirming the predictive power of these methods. Each virtual galaxy carries the imprint of its dark matter halo, highlighting the invisible framework that governs visible structures. The cosmic web, A vast network of filaments and voids emerges naturally in simulations with dark matter. Dark matter forms the backbone of this web, providing the gravitational scaffolding for ordinary matter to follow. Filaments connect dense clusters, while vast voids remain nearly empty. Observational surveys of galaxies show patterns that closely resemble these simulated structures. By matching the observed distribution of galaxies with simulated cosmic webs, scientists can infer properties such as halo mass, concentration, and substructure. The alignment of theory and observation strengthens the case for dark matter's central role in the universe. Simulations also help explain the internal dynamics of galaxies. The rotation of stars and gas, the stability of spiral arms, and the persistence of galactic disks all require dark matter. Without the gravitational influence of halos, galaxies would be prone to instability and disruption. N-body simulations demonstrate how dark matter halos absorb and redistribute energy during galaxy interactions, helping disks survive collisions and mergers. By tracking individual particles in a simulated halo, researchers can visualize how dark matter stabilizes galaxies over billions of years, providing context for the rotation curves observed in actual systems. Substructures within dark matter halos, known as subhalos, are also evident in simulations. These smaller clumps host satellite galaxies and influence tidal streams within larger galaxies. Observations of dwarf galaxies orbiting the Milky Way, along with stellar streams, confirm the presence of subhalos, consistent with simulation predictions. The distribution, mass, and behavior of these subhalos provide additional constraints on the nature of dark matter. If dark matter were warm or interacting differently, subhalos would be less abundant or exhibit different properties. Simulations therefore act as a bridge between theoretical particle physics and observable galactic phenomena. Simulations also allow scientists to explore extreme scenarios. Colliding galaxy clusters, the formation of massive elliptical galaxies, and the growth of the largest cosmic filaments can all be studied under controlled conditions. By altering the properties of dark matter, researchers can test how galaxies would form and evolve differently. These experiments show that dark matter's non-interacting, gravitationally dominant nature is essential for producing the observed variety of cosmic structures. Even subtle changes in particle properties lead to measurable differences in galactic rotation, cluster density, and cosmic web morphology. Through these models, scientists can also connect small-scale phenomena to the largest scales of the universe. Individual halos form galaxies, which aggregate into groups, clusters, and filaments. The same principles that govern the motion of particles in a halo apply to the evolution of clusters and the cosmic web. Simulations illustrate how dark matter operates across these scales, linking the behavior of single galaxies to the overall distribution of matter in the universe. By observing virtual universes evolve under different assumptions, astronomers gain insight into the essential characteristics of dark matter required to reproduce reality. Finally, simulations inform observational strategies. Predicting where dark matter is concentrated helps guide searches for indirect signals, such as gamma rays from dense regions or direct detection experiments on Earth. By knowing which structures to study and what signatures to expect, scientists can optimize instruments and observational campaigns. The interplay between simulation and observation is continuous. Each new measurement refines the models and each model suggests new ways to observe and test dark matter properties. This cycle drives progress, linking theoretical insight with empirical evidence. Through n-body simulations, the invisible becomes tangible. Dark matter is shown to sculpt the cosmic web, stabilize galaxies, form substructures, and guide the evolution of clusters. By comparing simulations with real observations, scientists confirm that dark matter's properties must be consistent with the large-scale universe we see today. These virtual experiments allow researchers to test candidate particles, study formation processes, and predict structures before they are observed. Simulations thus form a crucial part of modern astrophysics, providing a clear picture of how dark matter shapes the universe from the smallest halos to the largest filaments in the cosmic web. Despite the strong evidence for dark matter, scientists have also considered alternatives. Some researchers wondered whether the laws of gravity themselves might behave differently at very large scales. One of the most discussed ideas is called modified Newtonian dynamics, or MOND. MOND proposes that Newton's laws, which describe how objects move under gravity, need slight adjustments when accelerations are extremely small, such as at the edges of galaxies. By changing the relationship between force and acceleration in this way, MOND can explain why stars in the outer parts of galaxies move faster than expected without invoking invisible mass. MOND successfully reproduces the rotation curves of many spiral galaxies. By adjusting a simple parameter that defines when gravity transitions from normal behavior to the modified form, the theory can match the speeds of stars without assuming a halo of dark matter. This simplicity makes MOND appealing in some cases, and it demonstrates that modifications to gravity can sometimes mimic the effects attributed to dark matter. In particular, MOND works well for certain types of galaxies, predicting the velocity distribution across a disk using only the visible matter, which is impressive given the limited number of parameters in the model. However, MOND and similar modified gravity theories face limitations. While they can explain galactic rotation curves, they struggle to account for observations on larger scales, such as clusters of galaxies and the cosmic microwave background. In galaxy clusters, the amount of visible matter is insufficient to produce the gravitational lensing observed, even with modified gravity. Additional unseen mass is still required to explain the bending of light. Similarly, the CMB fluctuations are consistent with a universe containing substantial non-baryonic matter. MOND alone cannot reproduce the detailed patterns seen in the cosmic microwave background or the large-scale structure observed in the cosmic web. Other alternatives include extensions of general relativity that change how gravity behaves over long distances. Some theories introduce additional fields or forces that mimic dark matter's gravitational effects. These models are mathematically sophisticated and can reproduce certain observations, but they often require fine-tuning or introduce new unknowns. Every modification must be consistent, not only with galaxy dynamics, but also with gravitational lensing, cluster masses, cosmological expansion, and the distribution of cosmic structures. This broad set of constraints makes alternative theories challenging to maintain as comprehensive explanations. Despite the exploration of these alternatives, dark matter remains the leading explanation for the invisible mass in the universe. Its appeal lies in its simplicity and universality. A single component, interacting primarily through gravity, can explain phenomena across many scales. From galactic rotation curves to clusters and the cosmic web, dark matter provides a consistent framework that aligns with diverse observations. By contrast, modified gravity models often succeed in one context but fail in others, requiring additional assumptions to explain discrepancies. The consistency of dark matter across multiple lines of evidence strengthens its position as the prevailing explanation. Observational tensions do exist, however. Some galaxies show rotation curves or mass distributions that deviate slightly from predictions based on standard dark matter models. Certain small-scale features, such as the number and distribution of dwarf galaxies around larger galaxies, appear less abundant than predicted by simulations. These tensions have prompted refinements in simulations, consideration of baryonic feedback processes, and examination of alternative dark matter properties. While not undermining the overall dark matter framework, these challenges highlight areas where our understanding of galaxy formation and halo structure remains incomplete. Ongoing debates continue in both theoretical and observational astrophysics. Researchers question whether discrepancies arise from limitations in simulations, unaccounted astrophysical processes, or perhaps subtle properties of dark matter itself. For instance, some models propose warm dark matter with slightly higher particle velocities to explain the scarcity of small-scale structures. Others explore self-interacting dark matter, which could alter halo density profiles and reconcile certain anomalies. Each approach maintains the general concept of dark matter, while exploring variations in its behavior to better match observations. Gravitational lensing provides additional evidence that challenges modified gravity alone. Clusters, such as the bullet cluster, exhibit a separation between the visible matter, mostly hot gas, and the dominant gravitational mass revealed by lensing. This clear offset indicates that most of the mass is invisible and does not interact strongly with ordinary matter. Modified gravity cannot fully explain this effect without invoking some form of unseen mass, reinforcing the necessity of dark matter. Observational results like this have been pivotal in maintaining dark matter as the preferred model in modern cosmology. Another point of consideration is the cosmic microwave background. The CMB fluctuations depend on the total matter content, the ratio of baryonic to non-baryonic matter, and the behavior of gravity in the early universe. The observed spectrum matches predictions that include dark matter, while modified gravity without dark matter fails to reproduce the pattern. This consistency across both early and late-time cosmological observations further strengthens the case for dark matter over alternative gravity theories. It demonstrates that the invisible mass is not only relevant locally within galaxies, but also cosmologically, influencing the evolution of the entire universe. While alternatives like MOND spark interesting discussion and provide valuable insights, they are not sufficient to explain all phenomena. They highlight that our understanding of gravity and matter is incomplete, prompting careful consideration of the underlying physics. In some cases, hybrid approaches have been proposed, combining modified gravity with some form of dark matter, though these remain speculative. Such explorations illustrate the scientific process, testing ideas, comparing them to observations, and refining models to better match reality. Dark matter, however, consistently provides a framework that accounts for observations across scales without requiring ad hoc assumptions. The debate over dark matter versus alternative theories also drives experimental and observational programs. By identifying predictions unique to each model, astronomers can design tests that may confirm or refute competing ideas. For example, precise measurements of galaxy rotation curves, lensing maps, and the distribution of clusters can distinguish between modified gravity and dark matter scenarios. Future surveys of cosmic structures, combined with improved simulations, will continue to refine our understanding and potentially reveal subtle features that inform the properties of dark matter or the validity of alternative theories. Ultimately, the consideration of alternative theories underscores the complexity of understanding the universe. Gravity is the dominant force shaping large-scale structures, yet the unseen component of matter dominates the total mass. By exploring both modifications to gravity and the presence of dark matter, scientists probe fundamental physics in regimes inaccessible in laboratories. Observations, simulations, and theoretical models converge to reveal a picture in which dark matter plays a central, indispensable role, while alternative ideas serve as tests that sharpen our understanding and confirm the robustness of the dark matter framework. Alternative theories such as MOND offer valuable perspectives and succeed in explaining certain galactic phenomena. However, they face significant challenges when applied to clusters, gravitational lensing, and the cosmic microwave background. Dark matter remains the simplest and most consistent explanation for the invisible mass shaping the universe. Observational tensions highlight areas for further study, but the cumulative evidence from multiple scales and phenomena confirms dark matter's central role. The scientific process continues, with debates, refinements, and new data driving an ever deeper understanding of the cosmos and the invisible substance that governs its structure. Dark matter not only shapes individual galaxies and clusters, but also influences the universe on the largest scales. Its gravitational pull affects how the universe expands, how structures form, and how galaxies evolve over billions of years. From the earliest moments after the Big Bang, dark matter acted as a framework for matter to gather, forming dense regions where galaxies and clusters would eventually appear. Without this invisible scaffolding, ordinary matter alone could not have clumped efficiently. The gravitational influence of dark matter helps explain why the universe developed the rich structure of filaments, sheets, and voids we observe today. As the universe expands, dark matter continues to guide the motion of galaxies and clusters. While space itself stretches, the gravitational pull of dark matter halos slows the separation of galaxies within groups and clusters. These halos act like invisible anchors, keeping galaxies bound together even as the universe grows. The larger the halo, the more effectively it holds galaxies within it. This balance between cosmic expansion and gravitational binding determines the distribution of galaxies across space, creating the intricate web-like pattern known as the cosmic web. Observations of large-scale structure reveal filaments connecting clusters, with voids in between, all shaped largely by dark matter. Dark matter also influences galaxy mergers. When two galaxies approach each other, their dark matter halos interact first. These halos can absorb kinetic energy, allowing the galaxy's visible matter to merge smoothly over time. Simulations show that halos play a stabilizing role, preventing stars from scattering chaotically during collisions. The presence of dark matter enables the formation of larger galaxies through mergers, guiding the evolution from small proto-galaxies to massive ellipticals and the complex spirals we see today. Without dark matter, these mergers would be less efficient, and the population of galaxies might look entirely different. Star formation within galaxies is also indirectly affected by dark matter. Dark matter halos provide the gravitational potential wells that allow gas to cool and condense. As gas falls into these wells, it compresses and forms dense clouds, the birthplaces of stars. Regions with more massive halos tend to accumulate gas faster, leading to higher rates of star formation. Conversely, small halos may struggle to retain gas, limiting stellar activity. In this way, dark matter shapes not only the structure of galaxies, but also their internal evolution, influencing the distribution of stars and the emergence of galactic features such as spiral arms, bulges, and central bars. The interaction between dark matter and normal matter is subtle because dark matter barely interacts except through gravity. Unlike gas and dust, it does not cool, emit light, or undergo pressure-driven collapse. Its influence is purely gravitational, yet this is enough to dominate galactic dynamics. Ordinary matter responds to the gravitational landscape created by dark matter, forming stars and galaxies in regions defined by the underlying halos. Observations of galaxy rotation curves, cluster dynamics, and lensing maps all demonstrate that dark matter dictates the movement and distribution of normal matter, even though it remains invisible to direct observation. Over cosmic time, dark matter helps maintain the stability of large-scale structures. Clusters of galaxies, connected by filaments of dark matter, evolve in a hierarchical manner. Smaller structures merge into larger ones, guided by the invisible mass surrounding them. Filaments channel galaxies toward clusters, and voids expand as matter is drawn into denser regions. This process continues over billions of years, shaping the universe's architecture. The persistent presence of dark matter ensures that structures remain coherent, resisting complete dispersal due to cosmic expansion and preserving the large-scale pattern imprinted since the early universe. Dark matter also plays a role in the long-term fate of the universe. Its gravitational influence competes with the effects of dark energy, which drives cosmic acceleration. While dark energy pushes galaxies apart, dark matter binds them together locally. The interplay between these forces determines whether structures continue to grow, merge, or slowly drift apart. In dense regions, clusters may eventually stabilize, while in underdense regions, galaxies will continue to separate. The overall distribution and amount of dark matter influence the rate at which cosmic structures evolve and the degree of coherence that will persist over time. The distribution of dark matter impacts the survival of galaxies during interactions. When small galaxies pass near larger ones, the tidal forces exerted by the combined dark matter halos determine whether stars are stripped or remain bound. Satellite galaxies often orbit within the halos of larger galaxies, their motions governed by the unseen mass. Streams of stars stripped from these satellites trace the gravitational potential, providing observational evidence of the underlying dark matter. Such interactions continue to shape galaxies, creating streams, shells, and other structures that reveal the invisible gravitational landscape. Cosmic filaments, composed largely of dark matter, channel matter and energy across vast distances. Gas flows along these filaments, feeding clusters and fueling star formation. The geometry and connectivity of filaments influence the growth of massive galaxies and superclusters. Observations of galaxy alignment along filaments, combined with lensing maps, confirm that dark matter shapes the pathways along which matter moves. These invisible highways guide the assembly of matter on scales much larger than individual galaxies, illustrating dark matter's role in structuring the universe at multiple levels. Over billions of years, dark matter also affects the chemical evolution of galaxies. By influencing the rate of gas accretion and star formation, it indirectly shapes the enrichment of elements produced by stellar processes. Regions with more massive halos can sustain prolonged star formation, allowing successive generations of stars to create heavier elements. This process contributes to the diversity of chemical compositions observed across galaxies. Even though dark matter itself does not participate in these reactions, its gravitational guidance underpins the environments where such processes occur. In the very long term, dark matter will continue to influence the universe even as star formation slows. Galaxies may merge into larger systems, forming massive ellipticals, while some regions become isolated as expansion separates them from other structures. Dark matter halos will persist, maintaining the gravitational framework that keeps stars and gas bound. The invisible scaffolding will outlast luminous matter, which eventually fades as stars burn out. In this sense, dark matter shapes the enduring skeleton of the universe, maintaining structure even in the far future when ordinary matter becomes less visible. Simulations of the distant future suggest that dark matter halos will remain the dominant mass in the universe, preserving galaxy clusters and superclusters as coherent systems. Stars may die, and gas may cool or be expelled, but the halos will continue to exert gravitational influence, maintaining the organization of bound structures. Filaments will stretch and thin under cosmic expansion, but the dark matter within them will keep the matter along these structures gravitationally tethered. The universe's ultimate architecture, long after visible light has faded, will still reflect the distribution of dark matter that developed over billions of years. Finally, dark matter's persistent presence shapes the context in which any future cosmological events will occur. Supernovae, black hole mergers, and other energetic processes unfold within galaxies governed by halo dynamics. The pathways of matter, the locations of dense regions, and the interactions between galaxies are all guided by the invisible gravitational influence. By shaping the large-scale and small-scale behavior of matter, dark matter acts as a constant, silent force, orchestrating the cosmic ballet and ensuring that the universe evolves in a coherent, structured manner over immense spans of time. Dark matter determines how galaxies form, merge, and survive. It guides the flow of gas, shapes star formation, and maintains the stability of clusters and filaments. Its gravitational presence resists cosmic expansion locally, preserves structure, and influences the long-term evolution of the universe. While invisible and non-interacting in ordinary ways, dark matter exerts a subtle but decisive control over cosmic destiny. From the earliest clumps to the vast cosmic web and the future of galaxies, dark matter's influence is fundamental, shaping the past, present, and future of the universe in ways that are both profound and enduring. Even after decades of study, dark matter continues to reveal new subtleties as observational technology improves. Modern telescopes and surveys provide data of unprecedented precision, enabling astronomers to refine their understanding of dark matter's distribution and behavior. The Dark Energy Survey, for example, has mapped hundreds of millions of galaxies over a large portion of the sky. By analyzing the shapes and positions of these galaxies, researchers can detect the tiny distortions caused by gravitational lensing, revealing where dark matter lies. These surveys show that dark matter is not smoothly distributed, but forms a complex network of clumps, filaments, and voids that trace the cosmic web. The level of detail now visible allows scientists to measure halo masses more accurately and understand the internal structures of these invisible scaffolds. The European space mission Gaia has also contributed significantly to dark matter studies. While Gaia's primary goal is to chart the positions and velocities of stars in the Milky Way, the resulting data provide indirect evidence of the underlying dark matter halo. By mapping the motion of stars, especially in the outer regions of the galaxy, scientists can infer the gravitational pull of unseen mass. Subtle variations in stellar velocities reveal the presence of dark matter clumps and streams, which may be remnants of small satellite galaxies absorbed by the Milky Way. This detailed stellar cartography allows researchers to refine models of the galaxy's dark matter halo, improving our understanding of its shape, density profile, and substructure. Recent surveys have also uncovered subtle filaments of dark matter connecting galaxies and clusters. These structures, invisible to direct observation, reveal themselves through weak gravitational lensing, where the shapes of distant galaxies are slightly distorted by the mass between them and Earth. By statistically analyzing these distortions across millions of galaxies, astronomers can reconstruct the invisible mass distribution on scales of tens to hundreds of millions of light-years. These filaments not only provide insight into the large-scale organization of matter, but also help explain how gas and galaxies are channeled along these structures, influencing star formation and cluster growth. Observations of halo mass and distribution have become increasingly precise. By combining lensing data with stellar motions and galaxy clustering, scientists can map the density of dark matter across different environments. Dense halos surrounding massive galaxies and clusters are clearly resolved, while less massive halos hosting dwarf galaxies are also detectable through their gravitational influence. These refinements are essential for testing theories of dark matter and for comparing results with cosmological simulations. The match between predicted halo properties and observational measurements strengthens confidence in the cold dark matter model, while deviations hint at areas where further investigation is needed. Multi-messenger astronomy, which observes the universe through different channels such as light, neutrinos, and gravitational waves, has opened new avenues for understanding dark matter. Neutrino astronomy, for instance, explores how these nearly massless particles interact with dense regions of dark matter. High-energy neutrino detectors, like IceCube at the South Pole, can detect neutrinos originating from the Sun or the centers of galaxies, potentially produced by dark matter annihilation. While no definitive signal has been confirmed, combining neutrino data with optical, infrared, and gamma-ray observations allows scientists to place tighter limits on dark matter properties and explore scenarios beyond simple particle models. Gamma-ray observations complement these efforts. Space-based telescopes such as Fermi-LAT monitor the sky for excess emissions from regions of expected high dark matter density. By comparing gamma-ray maps with gravitational lensing results and stellar motion data, researchers can cross-check predictions of dark matter distribution. This integrated approach reduces uncertainties and helps distinguish dark matter signals from other astrophysical sources. Observations of dwarf spheroidal galaxies, in particular, are valuable because these galaxies are dominated by dark matter and contain little gas or stellar activity that could complicate measurements. Recent work has revealed that dark matter halos are not smooth, but contain smaller subhalos. These clumps can host tiny satellite galaxies or remain largely dark. Observationally, these subhalos affect the motion of stars, the formation of stellar streams, and subtle distortions of background light. Detecting and mapping these substructures provides insight into the hierarchical assembly of galaxies and the nature of dark matter particles. For instance, if subhalos are less abundant or differently distributed than predicted, it may indicate that dark matter has different properties than assumed in the standard cold dark matter model, such as being warmer or self-interacting. The refinement of halo mass estimates is aided by advances in computational modeling and statistical techniques. Surveys now collect data on millions of galaxies, requiring sophisticated algorithms to extract meaningful signals. Weak lensing studies combine the shapes of many galaxies to detect minute distortions, allowing the reconstruction of halo density profiles over large areas. By integrating these results with stellar kinematics and other observational traces, astronomers achieve detailed three-dimensional maps of dark matter distribution. These refined maps inform both theoretical models and simulations, providing a bridge between observation and theory. Observational advances also clarify the relationship between dark matter and ordinary matter. By comparing galaxy properties such as luminosity, gas content, and star formation rates with the mass and shape of their halos, scientists gain insight into how dark matter influences galaxy evolution. Denser halos tend to host more massive galaxies, while smaller halos may correspond to low-luminosity dwarfs. Studying these correlations helps constrain feedback processes, such as how supernova or active galactic nuclei interact with gas, and how dark matter guides these processes through its gravitational influence. The combination of optical, infrared, and X-ray surveys provides complementary information about dark matter in clusters. While lensing traces total mass, X-ray observations detect hot gas, and optical surveys map galaxies. The comparison reveals that most of the mass in clusters is dark, with the visible components contributing only a fraction. These studies also uncover complex features, such as merging subclusters and elongated filaments, which reflect the gravitational influence of dark matter. By observing these structures over time, astronomers can trace the assembly history of clusters and refine estimates of halo mass and concentration. In addition, recent observations suggest that dark matter may influence the paths of high-energy cosmic rays. Cosmic rays traveling through regions of dense dark matter may be subtly deflected or experience different propagation patterns due to gravitational effects. While these effects are small, they provide another potential tool for probing dark matter structure. Coupled with neutrino and gamma-ray observations, this multi-messenger approach expands the ways in which invisible mass can be studied, combining different observational methods to gain a more complete picture. Studies of nearby galaxies also reveal the presence of dark matter substructures and streams. These features often result from past mergers or interactions with smaller satellites, leaving trails of stars and gas that trace the gravitational influence of dark matter. Observing these features allows scientists to infer the shape and density of the surrounding halo, offering insight into the hierarchical formation process. Subtle asymmetries or disruptions in stellar motions serve as natural probes of otherwise invisible mass, making detailed observations of local galaxies a powerful tool for dark matter research. These recent discoveries demonstrate the increasing power of collaboration between surveys, telescopes, and detection methods. By integrating gravitational lensing, stellar kinematics, gamma-ray and neutrino data, and multi-wavelength imaging, astronomers build a coherent picture of dark matter's distribution and behavior. Each new observation refines models, constrains particle properties, and improves simulations. The interplay between observation and theory continues to illuminate the invisible universe, showing that dark matter is both complex and fundamental, shaping cosmic structure in ways that are now observable with increasing clarity. As we step back to observe the universe on the largest scales, it becomes clear that dark matter is the invisible scaffold supporting everything we see. Galaxies, clusters, and vast filaments are all drawn together and held in place by the gravity of this unseen mass. Light travels across the cosmos, revealing stars and nebulae, but the structure behind that light is shaped largely by something we cannot touch or directly see. Dark matter does not glow, it does not absorb, and it does not collide with ordinary matter in the ways we expect. Yet it dominates the cosmic landscape, forming the framework upon which visible matter organizes itself. Without this invisible presence, the universe would look entirely different, less structured, less coherent, and far more chaotic. The scale of dark matter is immense. Each galaxy sits within a halo that stretches far beyond the visible edge of its disk. Clusters of galaxies are embedded in halos that extend millions of light years, connecting through filaments to form the cosmic web. Even the emptiest regions, the voids that seem so desolate, are defined by the pull of nearby dark matter structures. It shapes motion, governs interactions, and guides the formation of new stars and galaxies. Across billions of years, the gravitational influence of dark matter has allowed ordinary matter to clump, merge, and evolve into the variety of cosmic structures that fill the night sky. Every spiral, elliptical, and irregular galaxy owes its existence and stability to this hidden substance. The mystery of dark matter is profound. For decades, scientists have measured its effects, traced its halos, and observed its fingerprints in lensing, rotation curves, and cosmic microwave background fluctuations. Yet, despite knowing it exists and understanding its influence, the fundamental nature of dark matter remains elusive. Is it a particle, or a collection of particles we have yet to detect? Does it interact in ways so subtle that even our most sensitive instruments cannot observe? The universe demonstrates its presence through motion and structure, but the material itself continues to evade direct observation. This combination of certainty and mystery imbues the cosmos with a quiet depth, showing that the unseen can govern the seen. From a human perspective, this is humbling. We gaze at the stars, the galaxies, and the glowing nebulae, appreciating the light that reaches our eyes. Yet, The forces holding those luminous objects together and guiding their evolution lie hidden. What we see is only a fraction of the cosmic story. The patterns of motion, the shape of spirals, the clustering of galaxies, all are dictated by matter that cannot be touched or seen. Dark matter teaches a lesson in perspective, that the visible is supported and sustained by the invisible, and that understanding the universe requires looking beyond light and color to the deeper, silent structure beneath. This invisible scaffold is not static. It moves, shifts, and evolves, guiding galaxies as they collide, merge, and grow. Streams of stars, remnants of past interactions, trace the gravitational contours of dark matter halos. Filaments connect clusters, providing highways along which gas and galaxies flow. Voids expand, shaped by the gravitational tug of surrounding structures. Dark matter provides coherence across scales, from the smallest dwarf galaxy to the largest supercluster. Its influence is gentle yet persistent, pervasive yet hidden, creating an intricate cosmic tapestry that unfolds quietly over billions of years. As we reflect on this, it becomes natural to see dark matter as a gentle presence rather than a force of chaos. Its gravity shapes motion without friction, guides growth without interference, and holds galaxies together without visible hand. It provides the conditions necessary for stars to shine, for planets to form, and for the complex structures we observe across the universe. Each twinkling star owes its place to the silent framework of dark matter, each galaxy's spiral arms to the guiding pull of an unseen halo. The cosmos is both bright and shadowed, illuminated by what we see and structured by what we do not. In a sense, dark matter embodies the quiet persistence of the universe. It operates on scales far beyond human comprehension, yet its effects are intimate, shaping the environments where stars, planets, and life itself emerge. We live on a small planet, orbiting a star, inside a galaxy nested within a vast halo of invisible mass. The night sky appears serene, but beneath that serenity is a carefully structured cosmos, held together by forces we can measure but not touch. Dark matter reminds us that the universe is more than appearances. Its true nature is hidden, yet its influence is undeniable, offering both scientific fascination and a kind of poetic wonder. As we close our eyes and let the mind drift over the cosmos, it is comforting to imagine this invisible scaffold at work. Galaxies rotate gracefully, clusters form and evolve, and filaments channel matter across immense distances, all silently guided by dark matter. There is a rhythm to these motions, a quiet order beneath the apparent randomness of stars scattered across the sky. It is a gentle reminder that even in the vastness and darkness of space, structure exists, guided by forces that operate unseen, shaping the universe with calm persistence. For a bedtime reflection, we can appreciate both the light and the darkness, the seen and the unseen. Dark matter allows the universe to be vast, organized, and enduring. Its mystery invites curiosity, while its influence provides coherence. As we let our minds wander through cosmic scales, we can imagine stars and galaxies moving gracefully, held together by a silent, invisible hand. The universe is larger, stranger, and more intricate than the eye can perceive. And in this understanding, we find a sense of wonder, a quiet awe, and a gentle conclusion. That the visible cosmos is only part of the story, held in place by the invisible scaffold of dark matter that surrounds and shapes everything.